Now today we are dealing with first chapter, atomic structure and wave mechanics. John Dalton considered that all matter was composed of small particles called atoms. He showed that atom as a hard solid individual particles. These subatomic particles are called fundamental particles. The number of subatomic particles now known is very large. The three most important fundamental particles are proton, neutron, and electron. The main landmarks in the evolution of atomic structures are Thomson's discovery of electron and proton, Rutherford nuclear atom, Moseley's determination of atomic numbers, Bohr's atom, Bohr-Bury scheme of electronic arrangement, and Chadwick's discovery of electron. First we discuss about quantum theory of radiation. The wave theory of transmission of radiant energy appeared to imply that energy was emitted or absorbed in continuous wave. Max Planck studied the spectral lines obtained from hot body radiations at different temperatures. According to Planck, light radiation was produced discontinuously by the molecules of hot body, each of which was vibrating with specific frequency. The general quantum theory of electromagnetic radiation may be stated as: first assumption of quantum theory is when an atom or molecule absorbs or emits radiant energy, they do so in separate unit of waves called quanta or photon. Light radiation are not a continuous wave like this, but light radiation consists of stream of photon or unit of bundle, one unit, second unit, third unit. This individual unit is called photon or quanta. Thus, light radiations obtained from excited atom consist of a stream of photon, and it is not a continuous wave, it is a discontinuous wave like this. Second assumption of quantum theory, energy of a quantum or photon is given by E is equal to h nu, where nu is a frequency of radiation and h is the Planck constant, which has a value 6.62 into 10 raised to minus 27 arc second. We know that c is the velocity of light, and also we have nu is equal to c by lambda. Therefore, above equation becomes E is equal to hc by lambda. From this equation, it is clear that magnitude of quantum or photon of energy is directly proportional to the frequency of radiant energy, or is inversely proportional to its wavelength. Now, third assumption or third postulates of quantum theory is an atom or molecules can emit or absorb either one quantum of energy h nu or any whole number multiple of this unit. Thus, radiant energy can be emitted as h nu, 2h nu, 3h nu, and so on, but never as 1.5 h nu, 3.27 h nu, etc. This is all about Planck quantum theory. Now, today we discuss about photoelectric effect. When a beam of light of sufficiently high frequency is allowed to strike a metal surface in vacuum, electrons are ejected from the metal surface. This phenomenon is known as photoelectric effect, and ejected electrons are photoelectrons. For example, when ultraviolet light strike the surface of cesium, lithium, sodium, potassium or rubidium, all are alkali metals, in apparatus as shown in figure, which shows the photoelectric effect. This is the alkali metal lithium, sodium, rubidium, cesium, etc. When ultraviolet light strike the surface of metal in this vacuum, then electrons ejected from this surface. This effect is called photoelectric effect, and ejected electrons are photoelectrons. Due to photoelectrons, current flow through this circuit. Current is measured with the help of ammeter, and this figure shows the apparatus used in photoelectric effect. With the help of this photoelectric apparatus, the following observations can be made. First observation is, an increase in intensity of incident light does not increase the energy of the photoelectron. Means it shows increase means only increase their rate of emission. And second observation from photoelectric apparatus is, the kinetic energy of photoelectron increases linearly with frequency of incident light. If the frequency is decreased below a certain critical value, that frequency is called threshold frequency. Threshold frequency is the frequency required to eject the electron. That frequency is called threshold frequency, which is denoted by nu zero. The classical physics predicts that kinetic energy of the photoelectron should depends on the intensity of light and not on the frequency. Thus, it fails to explain the above observation. Now, Einstein explained photoelectric effect. Einstein explanation of photoelectric effect. According to Einstein, a photon of incident light, its energy means h nu to an electron in the metal surface which escape with kinetic energy half mv square, greater the intensity of incident light merely implies greater the number of photons, each of which release one electron. This increases the rate of emission of electron while the kinetic energy of individual photon remains unaffected. Second point, in order to release an electron from metal surface, the incident photon has first to overcome the attractive force exerted by the positive ion of the metal. In any metal, these are the delocalized or free electron, and M plus stands for positive ion core. There is a attraction between positive ion core and electron. When ultraviolet light strike the metal surface, first light break the attraction between this positive ion core and electron. After that, electron eject, and that electron is photoelectron. The energy of photon h nu is proportional to frequency of incident light. The frequency or the frequency required to eject the electron, that frequency is called threshold frequency, denoted by nu zero. For higher frequencies, nu is greater than nu zero. A part of energy goes loosen the electron and remaining impart kinetic energy to the photoelectron. Thus, h nu is equal to h nu 0 plus half mv square. Half mv square is the kinetic energy, where h nu is the energy of incoming photon. H nu is the minimum energy of electron escape from the metal surface with half mv square kinetic energy. The H nu 0 is a constant for particular solid, and it is termed as work function. Therefore, this equation becomes half mv square is equal to h nu minus w. This w is the work function. If we plot a graph frequency of incident light against kinetic energy of photoelectron, we get a straight line, and corresponding value on this axis, this is the threshold frequency. This is the equation for a straight line was experimentally obtained. Its slope equal to h, that is Planck constant. The value of h found come out to be the same was given by Planck himself. Now there is another effect, Compton effect, which shown only by graphite with the help of X-ray. Compton said that it was like a ball hitting a stationary ball which is pushed away while the energy of striking ball decreases. Compton showed that a photon of incident light struck a stationary electron in graphite and hence lost some energy, which is resulted in the increase of wavelength. Incident beam and scattered beam. Incident beam ची wavelength lambda, scattered beam ची wavelength lambda plus d lambda. When X-ray strike the surface of graphite and scattered beam have longer wavelength lambda plus d lambda. This process could not have occurred unless light radiation considered as a particle or photon. By assuming photon-electron collision, an incident beam consists of photon and in this sample of graphite there is an electron. Here collision between photon and electron. By assuming photon-electron collision to be perfectly elastic, Compton found that shift in wavelength, हे जे काही डिफरन्स आहे इन्सिडेंट बीमच्या वेवलेंथमध्ये आणि स्कॅटर्ड बीमच्या वेवलेंथमध्ये, दॅट इज शिफ्ट इन वेवलेंथ डी लॅम्बडा. डी लॅम्बडा वॉज गिवन बाय द एक्सप्रेशन 2h d lambda is equal to 2h by mc sin square theta by 2. हे ट्रान्समिटेड बीम स्कॅटर्ड बीम यामधला अँगल दॅट इज थीटा. Where h is the Planck constant, m is the mass of an electron, c is the velocity of light, and theta is the angle of scattering. The expression shows that d lambda means shift in wavelength is independent of the nature of the substance and wavelength of the incident radiation. Here m is the mass of electron, c is the velocity of light. M into c means momentum. By knowing the value of lambda, we can calculate the momentum of ejected electron.